What did the triangle say to the circle? You're pointless, because there's no points. Let's see how useful these so-called pointless circles really are on competition problems. So starting off with the basics, the area of a circle is pi r squared. The circumference of a circle is 2 pi r, where r is the radius. And if we have arcs in a circle, so let's say we have, instead not the whole circle, but let's say an arc of a circle, so a degrees, then the area of the sector is a over 360 times pi r squared, and the length of this arc over here, the length of this arc is 2 pi r times a over 360. Okay, now let's try an example that uses these formulas in a more interesting setting. Okay, 4 congruent semicircles are drawn within the boundary of a square with side length 1. The center of each semicircle is the midpoint of the side of a square. Each semicircle is tangent to 2 other semicircles. Region R consists of the points lying inside the square but outside of the semicircles. The area of R can be written as A minus B pi, and that's what we're trying to find here. 4 congruent semicircles are drawn within a square. The center of each semicircle is midpoint, and we're asked to essentially find, I know there's another square drawn here, but we're asked to find the region, all of this region here. So that, this, basically all of these regions that are inside the big square but outside the semicircles. This square is just a square that's part of the diagram, but it's not actually part of the problem. But the reason we're going to draw these lines over here, like you can see here. We're going to draw these lines because that is the point of tangency. And notice how this does indeed form another square. It forms another square, and that square is over here. It's a different one. It's not the one in the original question. And basically, we're trying to find this total region area, all this red area here. So to do this, we're going to have to find, well, to do this, we're going to have to take the area of the big square and subtract off the areas of the semicircles. The area of the big square is, well, side length 1, it says, so just 1 squared equals 1. That's the area of the square. Now, what is the area of all of these semicircles? To do that, we're going to have to find the radius of those semicircles. R. Basically, they all have radiuses over there. Have a radius, and how do we solve for that radius is the question here. So notice how it says it forms the midpoints. Each semicircle is the midpoint of the side of the square. So this is half over here. And this is half over here, right? Because the side, this is 1, so each of those is half because x is a midpoint. The center of the semicircle is a midpoint. And similarly, that's half, and that's half. Okay, so this part is r, that part's r. How do we solve for r? Look here, this is a right triangle. Half, and 2r. Let's draw it separately so we can avoid the clutter. We've essentially got a right triangle here, half, r, and 2r actually. And notice here is that these two side lengths are equal and it's a 90-degree angle. So it's a right triangle, but it's a nice soft-faced right triangle, also known as a 45-45-90 triangle, right? Because these are both going to be 45 since the sum of angles is 180 and these two angles have to be equal. So by properties of 45-45-90, 2r is half root 2 divided by 2 to both sides. 2r is 1/4 of root 2. R is 1/4 of root 2, or root 2 over 4. So then, what is the area of one semicircle? Just one. Well, the area of a circle with radius r is pi r squared, which is pi times 2 over 16, which is 1/8 pi. That's the area of a circle with radius r. But a semicircle is half. So 1 over 16th pi. Okay, so then what is the area of all four semicircles? Four semicircles will have an area of 4 times 1 over 16 pi, which is 1/4 pi. So 1/4 pi is the area of all four of those semicircles. The area of the big square was 1. The area of the four semicircles was 1/4 pi. So the area of the region outside of the semicircles, but inside of the square, is 1 minus 1/4 pi. Okay. So let's actually explore another example. It's not listed here, but it's a cool little trick. So imagine we have two circles here. Both of them have radius 1. So, and the center of the first circle lies on the other circle, and it's the same thing otherwise. So this is the center of the first circle, it lies on the second circle. And similarly, the center of the second circle lies on the first circle over here, right? They both have radius 1. So they both have radius 1, right? So we have this condition here. All the radiuses are going to be 1. And what we're asked to find in this problem is what is the area of this region in between? Let's move that there a little bit just to make it more accurate. What is the area of the region here, this region here? So this is an interesting question, but the idea behind this is that there's a really cool trick. Like this is kind of curves. It's almost like two arcs, isn't it? So the key condition is they're both radius 1 and they both have equal radius. So what we're going to do here is we can draw. It's always a good idea to draw all the radii you know. So all the important radii are radii that connect to a point that's defined. This right here is a point on the first circle. So this is going to be equal to 1 since it's a radii. Also, from here to here is also going to be 1 because that's also a radii, the circle. Similarly, this is also a radii of the second circle. It's going to be 1. So how do we find the area of this region here? And it's called a lune. Sometimes it's called a lune. So the key idea to find the area of that center region is to break it up into pieces. So the key idea is first, let's imagine this arc. Let's imagine this arc over here. What's the area of that? Well, the key idea to find the area of this region is notice that 1, 1, 1. That's an equilateral triangle. 1, 1, 1. Another equilateral triangle, right? This is 1 over here. So 60, 60, 60 degrees because of the equilateral triangle properties. So notice here that this angle is 120 degrees, right? Total. So the area of that blue region is 120 by 360 times pi r squared. R is 1. That's the area of this blue region. This region, right? And this is just equal to 1/3 pi. Now, let's erase this line that we have here. We found the area of that region. Now consider this other region. How about this one? make it orange, this region here. What's the area of that region? Well, notice it's the exact same setup. It's going to be 120 degrees over here, right? This angle is 120, and it's an arc of radius 1. So 120 over 360 times pi times 1 squared equals 1/3 pi. Now, these regions combined, they make up, what do they make up? Let's see. They make up, it seems like, okay, so we covered all of this region, and then we cover all of this region over here. So we make up the whole arc, except we count this inside region 2 times, right? Let's imagine shading it in. Like this orange region would cover all of that, and the red region would cover all of this part here. So the part that's counted, the area that's counted, we're counting twice, is the region inside the region on the inside of that rhombus you see there, right? This region here. This part is counted 2 times. So what we have to do is now subtract the area of this rhombus. How do we find the area of a rhombus? Well, if you remember from a previous video, it's just a half the product of the diagonals. But another way of doing this is realizing that it's just 2 equilateral triangles of side length 1. So the area of this rhombic region is 2 times √3 over 4 side squared, which is 1 squared. Remember the formula we learned? Which is 2 times √3 over 4, √3 over 2. So that means that the area of the lune, which is this region here, is just the sum of the areas of these 2 arcs. So minus the area of the rhombus, which is 2/3 pi minus √3 over 2. And that is it for this one. This is the answer. So the key idea for these types of problems is trying to break it down into regions and then forming circular arcs and subtracting the non-circular arc regions. That's often a case. And this is a classic example of a lune, which is a cool concept in circular area. Now, let's move back and let's try this problem over here using a similar idea. Suppose points A and B lie on the circle with radius 4 and center O, such that AOB is 90 degrees. 90 degrees. Probably hot at O. 90 degrees is pretty high temperature. The perpendicular bisectors of segments OA and OB divide the interior into 4 regions. So a perpendicular bisector is just a line that's perpendicular and it goes through the midpoint. So that's why it's a perpendicular, because it's perpendicular, and a bisector because it goes through the midpoint. So it's perpendicular bisector. So these 2 quantities are equal, and these 2 as well. Dividing this into 4 regions, find the area of the smallest region. Wow. So that's interesting. We've got this really random region. It's not a circle. And it's a similar idea to the previous problem we just discussed of how we have to break it up. So we should try to do something similar here. We can maybe form a circular arc from this. Then we can maybe solve for this, right? So this is a random region. How do we form a circular arc? Okay, so first things first, we've got a radius of 4. Let's use that condition. 2, 2. We can remove this midpoint here. 2, 2. So both of these parts are 2 each. Similarly, this part is 2. And this part over here is 2. So we have to somehow find the area of the shaded region. So like we did in the previous problem, we have to try and construct arcs. Let's try if we can connect these 2 points over here. Okay, so what we essentially are doing here is we get this thing like that, the area of this arc. So what we can essentially see here is the area of the shaded region. So let's do that. Shaded region equal to area of arc, the area of the arc, which is, let's draw like that, minus the area of this region here. This, let's draw it here. This yellow region here, minus yellow, right? So this arc, aha, we know how to find area of arcs using our formula that we know. So this arc has an area of, well, to find the area of an arc, we need to know the angle, right? So how do we find out this middle angle right here? So we have perpendicular bisectors. Somehow we have to try and use that condition, maybe. Okay, so notice here how this line, it passes through this point, passes through a point here, and similarly this line passes through a point here. So that's one part of it, finding the area of the arc. And the second part of it is finding the area of the yellow region. Okay, so let's first find the area of the yellow region. So the key idea here is when you have shapes like this, the best technique is to break it up into multiple shapes. So what we can do is draw a line through here. And essentially what that does is now we've got two regions. We've got this region over here, and we've got this region over here, right? Both of those are triangles, and we know how to find the area of a triangle, half base height. So for the first triangle, we have half, for I'm talking about this triangle right now, half times the base, which is this length, half base times height. Now, what is the height? Well, notice that the height is the one that forms a 90-degree angle with the base. So this over here will be the height of this triangle. Half base height, and the height is 2. Okay, now for the other region, for this triangle over here, it's the same thing. Half of this base times the height, which is 2. So now what is this base here? How do we find this length here? So the key idea here is that the reason this is here is because of the intersection of two perpendicular bisectors. So essentially what we have to do is to find, let me draw it a little thicker so it's more clear. We're trying to find the base. The base is this over here. Base is this, marked in the diagram. So to find that region, to find that length, sorry, what we can essentially do is find this whole length over here and subtract off this part over here. So what is that whole red length? Well, that whole red length we can find using Pythagorean theorem. Well, I'm just going to write it as Qn. So we have Q. I'm going to use some notation here, even though I generally don't like to do that. But over here, it's probably just a bit easier. We have QR equal to Qn minus Rn, right? That's just saying the same thing. This part equals this whole thing minus this part. Now Qn, notice how Qn, 2, and this form a right triangle, right? But what about this? What is that length really? That's just the radius of the circle, and the radiuses of circles have length 4 because, right, radius 4 in the problem given. So that's 4. This part is 2. So this part over here, we can use Pythagorean theorem. Let's call that x. 2 squared plus x squared equals 4 squared. So x squared equals 16 minus 4, 12. X equals 2 root 3. So Qn is 2 root 3. And then Rn, what is Rn? Well, Rn is just the same thing as MO because this over here is a bunch of right angles, it's a square. this is the right angle, this is the right angle, and this is the right angle, and that means this is the right angle. Because it has to be a square in this case, because the sum of angles in a quadrilateral is 360, right? So 2 root 3 minus 2, that's going to be QR. Okay, so that's going to be the base. So then the total area of those triangles is this plus this equal to just 2 times the base. And 2 times the base equals, well, this is the same thing as base, so 4 root 3 minus 4. So that's the area of this piece. This is 4 root 3 minus 4. Oh, sorry, the other way around. Remember, I shaded that yellow earlier. This yellow region is 4 root 3 minus 4. Now, what is the area of that sector? Again, we have to do this, we have to find the angle. And let's erase some of this clutter. It's getting a little bit messy here. So remember, we had that this was 2, 2. And we're looking for essentially the sector over here. So we have to find this angle. How should we find that angle? Well, remember how we found that this was, let's erase this for now. Remember how we found that this over here is 4? Well, then, look here. 4, 2, right angle. Does that remind you of any special triangle we may have learned? Double, hypotenuse double the leg. Root 3 times the shorter leg equals longer leg. Yeah, that's a 30, 60, 90 triangle, right? Because we see that hypotenuse is double the shorter leg, so it's 30, 60, 90. And you can see that this angle will have to be 60, and the angle and the side length opposite 30 is the smallest side too. Okay, so that's 60, which means this is 30. Okay, that's great. Now, what about, we know this whole part is 60, but we need to find the angle QOP essentially. We need to find the central angle over here. So to do that, we can essentially, what we can do is notice that if this whole part is 60, all we need to do to find the central angle over here is subtract off this part over there. That part, what is the angle of that part over there? Well, here's a key idea. Notice how that angle is 60, right? Now, another thing we can do is construct another one of such triangles. So if we do this triangle over here, we have the same thing. This is also a radius, it's 4. And if let's ignore this for now. So 4, 2, that's double the ratio, and it's a right triangle. So it's again another 40, 60, 90 triangle. So that means this angle right here is 60, and this is 30. Because we know that hypotenuse, double the leg, and right triangle means it's 30, 60, 90. So we know this angle is 60, and I'm going to bring this back. Remember, we discovered earlier that this angle over here was 60. Now, to find the central angle, it's just going to be equal to 30. Why? Because then all three of these parts are 30. All three of these parts are 30. And then this angle becomes 60. Remember, we calculated that earlier using this triangle, 30, 60, 90. And then this angle over here becomes 60 as well, which we also calculated using 30, 60, 90. So then the central part must be 30, so that the whole angle is going to be 90 degrees. And another way of seeing that is seeing that 60 plus 60 minus the central angle, right? You add both of them up, you subtract the central angle to get 90, so x is 30 from here as well. So there's two different ways to do that. So the angle is 30, and then we know that the radius of that circle is going to be 4. So the area of that circle is 30 over 360 times 4 squared pi, which is 1/12 times 16 pi, 4/3 pi. So the answer is just this quantity minus that, which is 4/3 pi minus 4√3 plus 4, and that's our answer for this problem. So the key idea here was noticing that this was just this thingy minus this region here. And then the inside region here was just two triangles. And to find the area of those two triangles, we just find base. And we found the base by taking the whole thing and subtracting this part, right? Remember how we found the whole thing using Pythagorean theorem or 30, 60, 90, and then subtracting this part. That's how we found QR, or the base of one of these triangles. And then both of the triangles are the same, so they have same base, same height. We found the area of this total region here that we're trying to subtract, the yellow region, we called it. So then the area of the smallest region is just the entire arc minus this part that we found here. And then we found the arc by just looking at the central angle using 30, 60, 90s. And the central angle we found to be 30. And then we found that this arc over here, we found the area of the sector over here to be 4/3 pi. We subtracted it out and got our answer. And that's next time we're discovering length in circles. You can check out the video where it's covered right over here.